This is video 1 of the Psych 642 non-parametric tests assignment. I'm going to begin this video by just giving a brief introduction to non-parametric tests, what they can do, when they should be used, how they work, and what they need in terms of data and assumptions. So non-parametric tests can do basically the same thing that the parametric versions of the test do. They just do it in a different way than the parametric test, which I'll get to in just a minute. But basically it boils down to all of these tests are comparing different groups. The Wilcoxon rank sum and the Wilcoxon sign rank test, both are comparing two groups. The difference there is whether it's independent measures or repeated measures. And then the Kruskal-Wallis, the Friedman-Zanova, and the Junkier-Terpstra tests, they're all testing three or more different groups. Once again, the difference there being some of them are independent measures and some of them are repeated measures tests. So as far as what they can do, it's once again the same for the most part as the parametric tests, and comparing different groups, with the exception of the Junkier-Terpstra test, which looks for trends. So what does make these tests different? These tests should be used specifically when the assumptions of parametric tests are not met. So the assumption for normality, the assumption for homogeneity, variance being two of the big ones there. That if those assumptions aren't met, then you would use this specific family of tests. So these tests work differently than parametric tests in that rather than using the data itself to run the analysis, all of the data are ranked from 1 to whatever the highest number would be, and then it's split into the different groups, and the differences in the ranks is what's compared there. So for example, with the Wilcoxon rank sum test, you're adding up the ranks in each group and then comparing that to see if there's a difference between the groups. So what this test needs as far as data is the same as its parametric counterparts as far as the types of variables. It does need categorical predictor variables. So if you're doing the Wilcoxon rank sum or the Wilcoxon sign rank test, that'll need to be a categorical predictor variable with 2 levels. And if it's the Kruskal-Wallis or the Friedman-Zanova, it'll need to be 3 or more levels. And then there will also need to be a continuous outcome variable. As far as assumptions, it has much fewer assumptions than the parametric tests do. We don't have to have normality, we don't have to have homogeneity, variance, but there are a couple of different assumptions that need to be met. The first of these is that all of these tests do require that there's a continuous distribution, which we just talked about in the data part, that the outcome variable has to be continuous. So there has to be a continuous distribution there. Additionally, it also makes the assumption that the distribution in the sample looks exactly like the distribution in the sample. So that sounds strange, but it's interesting because it's also necessarily true. But it is still an assumption. So now that we have gone over briefly what this statistical family is, and how and when to use it, I'm going to talk about what the research topic for this analysis will be. I'm going to be looking specifically at whether different types of therapy cause a change in anxiety scores. So, specifically, I'm going to be looking in the first test that I'm going to do, which will be the Wilcoxon rank sum. I'm just going to be looking at two groups, a waitlist control non-therapy group, and then a cognitive behavioral therapy group. In the second test that I'm going to run, which will be the Kruskal-Wallis, I'm going to be looking at three different groups, which will be the waitlist control, a rational emotive behavior therapy group, and a cognitive behavior therapy group. Since all of these different groups are going to be independent in that different subjects will get the different groups. It won't be the same subjects getting each condition. I will be using, like I said, the Wilcoxon rank sum and the Kruskal-Wallis because they're the independent measures tests, as opposed to the Wilcoxon sign rank test and the Friedman's ANOVA, which would have been the repeated measures versions. So that's the rationale for this test. I'm looking, like I said before, at differences between groups. I'll be using the Wilcoxon rank sum for the one that has 2 different levels, and the Kruskal-Wallis for the one that has 3 different levels. And I'll be using those two specifically because this is an independent measures. This is an independent measures design. So now I'm going to take a little bit of time to introduce the data set. So I'm going to go ahead and import both of those. Okay, so now that the 2 data sets have been imported, we can take a look at that. So you can see that there are as I mentioned, 2 different types of therapy in this first analysis, which will look at one group that's a waitlist control, and another group that got cognitive behavioral therapy, and then the anxiety scores listed in the second column here for that. The second set of data, as you can see, has 3 different types of therapy, and then anxiety scores set up in the next column corresponding to each participant's in each type of therapy. So now that the data has been imported, I'm going to open the R script file. I'm going to clear the console down here so that things don't get messy and confusing. And we'll get started with the analysis. So before I can do anything else, I have to load the packages that contain the functions that I'll need to complete the analysis. So I'm going to use the library function to load these packages. The first package is the clean_fun package. I'm going to go ahead and load it, but this is not one that I will be using in the analysis. It has the junkier Terpstra test in it, and I don't plan to use that, but it was involved with this chapter, so just in case it has something in it that I might need, I'm going to go ahead and load that. I'm going to load the ggplot2 just in case I need to do any graphs, which for this analysis I didn't do, but and then I'm also going to load the past ECS. This one I will be using definitely because it includes all of the functions for descriptive statistics. I'm going to be loading the PGIR-MESS package, which will have all of the post hoc tests functions that I'll need for the Kruskal-Wallis test in it. And then finally I'm going to do the CAR package, which has the function for Levene test in it. So I'll be using several of these, but not necessarily all of them. But they all relate specifically to this topic, so I went ahead and loaded them. So let me go ahead and do that. Okay, so everything is now loaded and ready to go. So next I'm going to just attach the first data set so that it can be used in the analysis. Then I'm going to get some descriptive statistics and also test for the assumptions of normality and homogeneity of variance to see if it's necessary to run a non-parametric test as opposed to a parametric test. So I'm going to use the by function and the stat.desc function in combination to get the descriptive statistics on anxiety scores for each therapy group. So I'm going to go ahead and run that. Which you can see, it's been broken down by group, and it gives all the pertinent descriptive statistics. Next, I'm going to use the by function again, but this time pair it with the Shapiro test function to test for normality of anxiety scores in each group of therapy. And we can see from this that neither of the groups appear to deviate from the normal distribution significantly, so it does meet the assumption of normality. And last, I'm going to use the Levene test function to test the assumption of homogeneity of variance. And you can see, put the outcome and predictive variables in here to specify what it is this function is supposed to be looking at. And here we see that there is a significant Levene's test, which means that the assumption of homogeneity of variance is not met. So it is necessary to use non-parametric tests, or it is appropriate to use a non-parametric test in this specific situation because of the lack of homogeneity of variance.